Greetings, everyone. I want to go over, that's chapter 8, right? Sorry, I forgot the number of the chapter, but I think it's chapter 8, Laplace transforms. And what I want to focus on what is important. So it's a review, right? So, of course, it's not a... don't just look at this video. It's kind of a summary of the videos on Laplace transform. And so we have this Laplace transform that to a function f, we get a capital F, we sometimes denote this in this fashion. And we do this especially when we trying to solve a linear a differential equation, capital Y. Now, I'm not going to concern myself with the actual definition of the Laplace transform, because we don't really need that. What we need is a kind of a table of these Laplace transforms, and there's really three things. Okay, other than the fact that they are they go through sums. The sum of a trust Laplace transform is the sum of the Laplace transforms, and linear combinations, not products, because that's the convolution. But the main thing is, what is the Laplace transform of t to the power n? So our functions will be here powers in variable t, and the Laplace transform is always written in our book here as function in terms of s. And so that is 1 over s n plus 1, and then on top we get an n factorial. Okay, that is the first major source of Laplace transform. The other one is the cosines. Cosine omega t is that's the variable, right? So it's t blanking, t squared plus omega squared, okay? And then the Laplace of sine omega t is omega t squared plus omega squared, okay? Sorry, just want to make sure here. Oh, I see why I got. I said I don't recognize it. Why did I recognize it? Because I was writing it with t. It's with s that I have to write it, right? S square, and here s square. Okay. Be careful for this little omega here, right? So because what is important, actually even more important than reading these tables this way, is reading the tables the other way. Because that is how we going to use Laplace transform. So what we do is, so that is one of the formula. And then sorry, I said 3, right? I didn't. This is 2 only. These 2 are the trig functions are both one part. But the most important thing is now the shift. So AAT results in a shift S minus A. So what does that mean? For instance, that the Laplace transform of AAT to the n will be n factorial, but not s, but s minus a to the power n plus 1. And the Laplace of EAT cosine omega t will be the same, but we now shift this way. And this tells us that any, and the same for the sine, right? That these are quadratic irreducibles, and any quadratic irreducible denominator we can now write in Laplace transforms. Okay, that's for going backwards. This is important. Okay, and then we have the rules that are that we also use. The other rules that are important here are what happens with derivatives, and that is sy minus the initial condition, and Ly double prime is s square y minus s times the initial condition minus the derivative, the initial condition at the derivative. So these are the 2 formulas that we then use, and that allows us to transform at least constant coefficients. So this, so if it's for the application to integration is always to constant coefficients. And we only do second order, but I don't know whether you noticed, but in fact you can do this in any order. You could, and in principle. But let's focus only on quadratics, because this is, we know very well how to factor quadratics, which is important, right? So let's do an example. I think it's best to do an example here. Oh yeah, no, right. So I have to say one more thing, of course, and that is that the Laplace transform of a product, that we don't know, but the Laplace transform of a convolution product, that is the product of the Laplace. And the convolution product, that is also, this is a formula that you need, because I will ask you to write down as an integral, that is f z g t minus z dz. Now the formula is not so difficult, but you have to think a little bit when you're dealing with concrete functions, because you're plugging in z and you're plugging in t minus z. Okay? All right. So these are the formulas that we need to solve our differential equation. So here's I'm going to give you an example. Let's do y double prime plus 10y prime plus 34y equals f of t. For now I'm going to do f of t, and then later on I'm going to do f of t equal to the function 9e to the minus 5t. But let's not do this with this function yet. So I remember I did this also on the quiz, right? I kind of told you to wait to work out the convolution integral before you do the actual calculation. And I also need in this thing, because we need, see, this is a bit different, right? We need initial conditions. Of course, you can always write some letters A and B there, but when you want to find what is happening, we need to know what these are, because we're going to have to, we're going to use this, right? We need this in our formula to solve. So I'm going to give you y0 is 3, and the derivative at 0 is also 3. Okay. So step 1 is we take the Laplace transform. So we apply the Laplace transform. The Laplace of y double prime, that is s square y minus 3y, 3s, right? 3s minus 3. This is, the first 3 is y0, the second 3 is the y prime 0, plus 10 times sy minus 3, that's the y0, plus 34 times capital Y. Okay, and then of course on the other side we get this capital F, the Laplace of little f, which we don't know what it is, so we at the moment it is vague. Good. Then we solve for y. So we have s square y minus 3s minus 3 plus 10sy minus 30 plus 34y equals capital F. So we get s square plus 10s plus 34y equals F. Minus 3 minus 30 is minus 33, so that becomes minus 3s becomes 3s on the other side, and minus 33 becomes plus 33. Okay, and then we solve for y, and this is important, we do this in two different we split this up in two different types, because one will be an inverse Laplace with it giving me a convolution, and the other one is just doing the regular technique, just finding the inverse Laplace. Okay, so this is our function. Now we note step 2 is we need to write these guys as, we need to know what this is, okay? Because we need to Laplace transform, this is a partial fraction, this is a rational function, so we have to write it as partial fractions. So the first thing we need to do is factor this thing, but the discriminant of this thing is 0, negative, small is less than 0. So if that's the case, that means there are complex roots, but that's not useful for us, the complex roots. That is useful if you do the technique from chapter 5, there, because this is the characteristic equation, right? But there you need the roots, but here we don't need the roots. So what we need instead is, we need to complete the square. So because of this, we need to complete the square. So we only complete the square when there are complex roots, right? When the discriminant is less than 0. When the discriminant is positive, we really factor, and then we find the partial fraction. Now, although this, you might not like it so much, it's actually easier, because, okay, we have to do this, and the trick is always you separate the two s terms, and then you divide this by 2, right? So divide by 2, that gives me 5, and then you square it, and that gives you 25. But of course, if you plus 25, you have to subtract 25 here. So this is therefore equal to s plus 5, this 5, squared, and then this is 9, right? Plus 9. Okay. Now, since it's a quadratic irreducible and on top we have a linear, we actually have the partial fraction, except that this quadratic is centered at -5. It's written as a polynomial in s plus 5, so we should also do this with the top. So with the top, we write it, we use that s is the same as s plus 5 minus 5, right? And then we work out what is 3s plus 3. 3s plus 33 is this 3s plus 5. Minus 5. Let me write it really in steps, right? So there's 3s plus 5 minus 15 plus 33. So that is 3s plus 5 plus 18. Okay. But we also need the partial fraction for this guy. Well, that's it. That we have it as a partial fraction. It's just the constant on top. There is no s. We have to write this guy in as a polynomial in s plus 5, but 1 is a polynomial, so that's also done. Okay. So let me copy what I have. Y is capital F, and then this is the partial fraction s plus 5 squared plus 9. There's a times. And here we have the partial fraction. And we're going to split this now. 3 times s plus 5 squared plus 9 plus 18 s plus 5 squared plus 9. Okay. So what are we going to do? We're going to now the next step, the last step, no, not the last step perhaps, but is now to take the inverse Laplace. Inverse Laplace. Of course, that gives me little y here. A product becomes a convolution, right? So let me point that out. This product becomes a convolution. The capital F, well, that came from little f. And what is this? Well, here we have a is -5. Remember, when we shifting, the a is the shift factor, is always written s minus a. Okay, that is something, it's a small thing, but you have to pay attention to that. It's s minus a here, right? So here you see it here at work here in this. You see it here, right? Okay. But also we have an omega here. What is omega? Omega is this. Be careful. It's the square root of 9, so there's 3. Okay. Now we on top. Therefore we should also have a 3 for the sign, and we don't have it. So I have to write this as 1/3, and then what is the shift? E minus 5t, and then we have sine. Omega 3t. This is a 5. Okay, imagine sine 3t. Okay. That's the inverse Laplace of this guy. What's the inverse Laplace of that? Well, that's the cosine. So plus 3 times e to the minus 5t cosine 3t. And this one, we should write this perhaps 18. We can write it as 6 times 3, right? Because this now is the inverse Laplace of this guy is the sine, and we have a coefficient 6 in front of it, plus 6 times e to the minus 5t sine 3t. Okay, and then finally, if I ask you to do this, you should actually, so if you want, step 4, really spell out what this star is, this convolution is. It's the integral from 0 to t. You replace the variable, you put z in the first one, fz, and you put the variable t minus z in the second one. So we have a 1/3 e minus 5 t minus z sine 3t minus z. And let's put a lot of parentheses. And then these we can copy. We can put the e minus 5t out, and we get 3 cosine 3t plus 6 sine 3t. Okay. So that is how you work it out in general. But now, as in the quiz, I said, okay, now once we are this far, now let's make this concrete for this 9 e to the minus 5t. so now, I don't know what to say. So f of t is 9 e to the minus 5t. That's what I said it was. Where was it? Yeah, 9 to the e minus 5t. So work out for this function. Okay. This means we have to look at this integral here. That's the only thing really that we need to do. So in one of these videos, I forgot this. Of course, there's this tail that at the end we should not forget, right? But I'm just going to focus now on the convolution integral. So that is f. So we put this z in this function, 9e to the minus 5z. Then we have in 1/3 e to the minus 5t minus z sine 3t minus z dz. Oh, I forgot my dz. Very important because I need to know which variable it is I'm integrating with. Is it z or t? Because there are two. Okay. So we can simplify, of course. The 9 with the 1/3 becomes a 3. And then this one, it splits as e minus 5t, e minus minus e to the 5z, right? And see how nice it was? Actually, well, two things. First of all, this is a constant, because it depends only on t, so I can bring this out. So e to the, let me give myself a little bit more space here. So this is equal to, I bring out the 3, that's the 9 and the 3, right? I also bring out the e minus 5t. Then these two guys cancel each other out. And so I'm actually left with sine 3t minus z. It's not necessary, but I'm going to do this. Let's actually expand this. So this would be 3t minus 3z dz. This is an easy integral, but you have the one thing you have to be a little bit careful about. So let's think about what? Well, the antiderivative of sine is negative cosine. So negative cosine. And then the variable is not really a variable. It's 3t minus z. Now, the problem is if I would take derivative of this guy, as I've written it down, what would happen? There would be a derivative of the inside function. And we're taking the derivative with respect to z, of antiderivative with z, and therefore also derivative with respect to z. That would result in an extra negative 3. So I compensate by that, for that. So that is the antiderivative of the integrand, and now I have to evaluate this between 0 and t. Okay, so that's the thing that you have to be a little bit careful about. Now the minus cancels and the 3's cancel too. So what we have left is e to the minus 5t, and then we have to plug in t and 0 in this expression. So if I plug in t, I get cosine 3t minus 3t, that is 0, so I get 1. What happens if I plug in 0? So minus, now I plug in 0, I get cosine 3t, right? Because I'm plugging 0 in z, not in t. That's sometimes confusing, but that's where I plug it in, okay? So that's the result of this integral. So our solution, therefore, y is, well, that integral here, e minus 5t, 1 minus cosine 3t, plus that tail that we already had written down here. Here perhaps e minus 5t, 3 cosine 3t, plus 6 sine 3t. And that's the solution. Now I should warn you, and remember we did this also in the quiz, I then can also ask you to do the same question now, because this f is a forcing function that we know how to deal with if we are linear coefficients, second order with constant coefficients. That's from the previous review. I'm not going to do it, but if you do it, you get a solution that should be the same. But I want to point out something that happens in your Laplace. Sometimes you can have terms, look, this term here, let's look at this term, that's cosine 3t e minus 5t, and there's also one here, okay? So these two actually simplify. That is a bit strange. So sometimes people think that this is the solution of the homogeneous and this is the solution of the particular solution. No. That's not how these things work. Laplace transforms, kind of mix everything up, right? That's also why we have these initial conditions from the start, and therefore we only find one solution. This doesn't depend on any integration constants. The method of Laplace transforms, at least the way that we're doing it, does not involve any integration constant. We get one single solution because we have already from the start these initial conditions. Okay, so that is the only thing that I'm really going to ask you to do on the final. We have seen applications of Laplace transforms, which are very nice, but I'll keep that for your own curiosity, or if you want to look at those. So that's everything that we need to know about Laplace transforms, okay? But, I mean, I did only one example. There are many different cases, right? This was the case where we had the quadratic irreducible. There could be cases where it actually is two real roots, or even worst case, so to speak, when we have a double root, okay?